Hello, I am Professor John Kelly and this is the Weber Auto YouTube channel. Today we are going to learn about regenerative braking systems in hybrid electric vehicles and electric vehicles. I have a neat little demonstration I want to show you. I have a 2017 Prius Eco transmission back here. This is the P610 transaxle. And if you've seen any of my other 40 or so videos on hybrid and electric vehicles, a couple of them deal with this transaxle as far as how it works and the technology inside of it. But what we are looking at here is the driver's side half of the transaxle, and it's laying sideways. Now in the case, parallel to each other, I have two electric motors. We have motor generator 1 that's right here that hooks to this sun gear, and I can rotate it, as you can see. And then over here we have motor generator 2, and I can rotate it. Now if you're not familiar with motor generator 1 or motor generator 2, I have an example of one right here. This particular one is from a Ford hybrid electric transaxle from a 2005 Escape, but it's very similar to what you would find in about any other hybrid transaxle. This is the rotor of an electric motor. It has very strong permanent magnets inside of it, and the way it's oriented inside of this case here, it has a sun gear connected to the top of it, just like I have a sun gear connected to the top of the motor that's down inside of this case. Now this rotor spins inside of a stator, and the stator is also inside of this transaxle housing back here. It would be facing vertically like this with this permanent magnet rotor inside of it and free to rotate like I'm showing you back here. But the stator I want to show you has three big electrical connections right here, the U, V, and W phases. And if we look real close in here, you can see the copper wire windings. And we have a UVW, 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 and it just continues on and on around the entire stator frame, this metal part here. So the important thing to understand for this demonstration is we have three big coils of wire inside of the stator assembly in the transaxle with a permanent magnet rotor. There are 8 magnetic poles of north and south on here as we rotate it, and that spins inside of the stator. Okay, to understand what's going on here with the stator and the permanent magnet rotor spinning inside of it, I've got a little demonstration to demonstrate what's called electromagnetic induction. And basically what that means is that anytime there's a magnetic field crossing a wire or a coil of wire, it will induce or push current in that coil of wire. So as an example, I have a small coil of wire right here hooked to an old school amp meter, and this is an AC for alternating current amp meter. So if this needle goes this direction, we would have a positive amperage. If the needle goes this direction, we'd have a negative amperage. And now I've got a permanent magnet here, a horseshoe magnet, and I want you to notice that when I bring the magnet close to the coil of wire, the needle goes in one direction. You see it go over to the right, but if I pull it away from the coil of wire, it goes in the other direction. So as I approach the coil of wire with the magnet, the needle went in one direction. As I go away from the coil of wire with the magnet, the needle goes in the other direction. And as long as there's movement, we will have current. But notice as soon as I stop, there's no current. So the same thing is happening with the 3 coils of wire in the stator and the 8 sets of magnets rotating on that rotor of the motor that spins inside of it. So let's hook this little amp meter to the output of MG1 stator over here. The three wires here on this stator, the U, V, and W phases, have the equivalent connections right over here of the, except they're ordered differently, the V, U, and W connections for MG1's stator and the V, U, and W connections for MG2's stator. So let's connect this amp meter to the stator here and see what happens. All right, I'm going to rotate the rotor inside of the stator, and we should see the current alternating back and forth, alternating current, AC current. Okay, here we go. I'm just going to turn it real slow. And we can see it going back and forth. So as we turn the rotor, we are inducing an alternating current on the wires that leave the stator. So I've got it hooked up to 2 wires here. That's the same as hooking it up to, say, these 2 wires right here. But there are three wires at the same time that are connected. So let's hook up 3 wires and watch the voltage signal being generated on these 3 phases. So we'll bring in my Fluke 4425 oscilloscope here. We will connect our blue lead to the V phase, our red lead to the U phase, and the green lead to the W phase. And we will watch the output on the oscilloscope here as I rotate the rotor inside of the stator. Now, so I can rotate the rotor faster than I can by hand, I'm going to connect an electric drill motor to that sun gear and rotate it. I had to come up with a little adapter here to hook a socket to the sun gear with a couple of hose clamps and some pieces of a radiator hose. Okay, now I'll hook my drill motor up. This drill motor is going to bring this up to approximately 1000 RPM, but I'll bring it up gradually and we will watch the 3 voltage waveforms, the 3 phase voltages. Here we go. Went too high on the voltage. So there we're about 40 volts. Let me slow it down. My adapter's a little out of balance here, but it's doing the job. All right, I'm going to take a screen capture right there. Okay, so what we're looking at here, the blue colored trace is the V phase, the red is the U, and the green is the W. And you'll notice that they're almost in a sine wave shape, but not quite. I always heard that it was a sine wave, but it's not. It's a bumpy sine wave. And that may have to do with the configuration of the magnets in the rotor. These rotors in this latest Toyota transaxle have a different style of permanent magnet in them, and they're using what I've been told is a negative Hallbox cylinder to use less rare earth magnets and yet come up with a strong magnetic field the same way. But they're using 5 magnets in sort of a triangle shape configuration rather than 2 magnets in a V configuration. But in this screen capture, we are at 30 volts peak. And if we come down and look at our measurements here, we're at 60 volts peak to peak. Our frequency was roughly 60 hertz, 60.79 hertz at this screen capture, and our true RMS voltage was 20.5 volts. So each one of these colors of traces on the oscilloscope screen represents the voltage induced in the coil of wire related to that phase. So there are three of these. There are three coils of wire in the stator, and each one of those coils of wire has its own voltage induced on it. Now, as long as there's not an electrical load connected to these wires, these rotors, MG1 and MG2, can free spin. Now, we are talking about regenerative braking here. So as you are driving your hybrid vehicle or your electric vehicle and let off on the throttle, the vehicle goes into a coast mode. In other words, we're not using power from the battery to accelerate you down a hill as you coast down a hill, or as you just slow down as you let off on the accelerator pedal. Under those conditions, these rotors can just spin freely. Now, an electric vehicle is only going to have one motor, but most hybrid vehicles have two motors. Now, if you step on the brake pedal at all, or pull your transmission shifter into the B position for braking, then these motors no longer free spin. We use the voltages induced on those three-phase windings that we just looked at on the oscilloscope, and we connect those to an electrical load. Now, typically that load would be the high voltage battery in your vehicle. We would take the three-phase voltages, convert them back to DC, and run current back into the battery to charge it up. But when you put a load on these motors, when you're decelerating, it makes them harder to turn. So this is real easy to turn right now. But if I take a load, and I've just got a resistor right here. This is a 10 ohm, 10 watt resistor, and I'm going to connect it to the same two phases that we hooked our amp meter to. Now, we've already seen from our oscilloscope that we approach 50 volts when we bring this up to a higher speed. And if we have 50 volts and 10 ohms, that's 5 amps of current. 5 amps of current times 50 volts gives us 250 watts that this 10 watt resistor would have to be dissipating. But of course it can't, so it's going to get really hot and probably burn up. So let's watch what happens here. I want you to listen to the speed of the drill motor, watch the speed of the rotor itself here, and let's watch the resistor here also. We'll see if we can let the smoke out. Now remember, this is only with 50 volts. These motors spin clear up to maximum 17,000 RPM and 600 volts. Okay, here we go. All right, I'm holding the drill motor at a steady speed. I'm going to connect the wire now to the resistor. Motor slows down. Every time I put a load on that stator by connecting this wire up here, the motor slows down. Now let me leave it connected. We'll speed it up some. And as you can see the smoke coming out, we were exceeding the the wattage rating of the resistor. The wires are not hot, but that resistor is certainly hot. So what we just saw there is what happens with regenerative braking. Instead of a drill motor turning the rotor inside of your transmission on your electric or hybrid vehicle, the tires through the half shafts, through the final drive differential, are turning the motor as you decelerate. It's mechanically turning the motor. And then the three-phase voltage output that we've looked at on these three wires is then run through a rectifier bridge, converted to DC, and put back into the battery. But we can, through the inverter assembly under the hood, change the resistance of the load that is connected to the stators here. So we can have a high resistance to where it's almost an open circuit and spins freely, or we can really turn up the charge rate by decreasing the resistance and make it really hard to turn. Now, why is it hard to turn? Well, because when we put a load on the output of these wires, we are causing current to run through the three-phase coils of that stator. And that current, remember, as we saw with the amp meter, is an alternating current. It's going positive, negative, positive, negative. Every time the voltage increases and gets positive, it creates a magnetic field around the stator itself. And then when the voltage decreases and goes negative, the field collapses. And that pulsating magnetic field, as it collapses, as the voltage decreases, creates an opposite polarity magnetic field to the rotational polarity of the magnets in the rotor, which means the stator windings will create the equivalent of a north pole that is facing the north pole of the rotor as it tries to rotate. And if you've ever played with magnets and you try to push two north poles together, it doesn't like it. So the higher the current in the stator coils of wire, the stronger the repulsive magnetic field is to allowing the rotor to spin inside the stator itself. And so it mechanically, through an electromagnetic field, through like magnetic poles repelling each other, it mechanically slows the vehicle down without using the hydraulic brakes very much at all or at all. In most cases, the hydraulic brakes under light braking aren't used until the lower vehicle speeds. The regenerative braking does the majority of the stopping. But of course that depends. If you're doing a panic stop, you'll get kind of a mix of regenerative braking and hydraulic braking. Now on the transmissions, that shifters that have the B position for braking, that turns up the charge rate. It gives us a smaller resistance, and of course that generates a lot of heat, which is why the inverters are liquid cooled, have their own radiator section and coolant to keep them cool. But on hybrid vehicles with two electric motors, on most of them that I've read about, when you pull the transmission into the B position, it uses both electric motors for regenerative braking rather than just the big MG2 that drives the vehicle. And then when you don't have the transmission in the B position and you let off on the accelerator pedal and just slow down, then it just uses the one electric motor, the drive traction motor, the MG2 or motor A, motor 1, whatever it is, depending on whether it's or whose brand of hybrid it is. Now there's one other thing that can affect regenerative braking, and it's something called negative torque. So normally when you accelerate, the DC voltage from the battery is converted to AC voltage to drive these motors. But when we decelerate, as you just saw, we induce our own voltages onto these windings, but it's opposite polarity voltage to the voltage that is used to drive the vehicle. So let's say we're inducing 50 volts in opposite polarity when we decelerate. If we use the inverter and we also try to accelerate at the same time with 50 volts versus 50 volts, they're equal and there would be no current and there would be no regenerative braking. So we can use the inverter to create a voltage that opposes the induced voltages from the stator and control how much voltage we apply versus how much we don't apply, which is the same as having a variable resistance here. So that is how regenerative braking systems work, according to my understanding. So the last thing I want to show you is if we take the three-phase voltages induced on MG1's stator and we connect them to the three-phase windings of MG2, what will happen? So let's try that. Let me grab some jumper wires here. I'm going to connect the V phase from MG1 to the V phase of MG2, and then the same thing with the U, and the same thing with the W. So when I turn MG1's rotor, its magnets induce three-phase voltages onto these three wires, and that simulates what the inverter assembly does up underneath the hood on most hybrids. Those three-phase AC voltages then are applied to our traction motor, MG2, and it drives the motor. So let's watch. Watch the direction of rotation and the speed as I turn MG1. Watch MG2. So notice MG2 spins with MG1 in the same direction. And once again, I'm simulating with MG1 what the inverter assembly does. DC to AC driving the AC motor. So we're using a set of spinning magnets to induce voltages on the three-phase windings of MG1 stator that create a three-phase voltage signal, just like the inverter does, that then runs current through the three-phase windings of MG2, which creates pulsating magnetic fields that pull and attract the sets of magnets in the MG2 rotor and pull it around. So we're using a magnet to induce voltages, we're using a voltage to pull a magnet, which is what the inverter assembly does. Now, if we reverse the U and the W leads over here, that's the same as putting your transmission in reverse. So to go in reverse now, notice I'm still spinning in the same direction MG1, but now notice MG2 is spinning backwards. And we do that just by reversing those two phases. So if I put them back to their original phase, notice now we're spinning in the same direction. So that's some pretty cool stuff to see. So what's cool about this to me is that this is a 2017 Toyota Prius transaxle, the P610, that normally runs on up to 600 volts. At bare minimum, it runs on a little bit less than battery voltage, which is around 201 to 207 volts, depending on which battery you get. But if we hook a voltmeter up here and look at the voltages induced on these wires, as I rotate this by hand, notice we're only getting 3 volts. 3 volts is all, which is incredible. The efficiencies of these motors is amazing for this to even work on 2 or 3 volts. So right here we are able to demonstrate how a hybrid electric transaxle or an electric transaxle with just one motor works without endangering ourselves, which is a pretty cool thing. So now I need to finish putting this transaxle back together and get it in the Prius, and we'll have another video when it's all in and working again. So this has been a demonstration of 3 different things related to regenerative braking. One, we saw the 3-phase voltage output on the oscilloscope and how the electromagnetic induction on 3 coils of wire creates a 3-phase voltage. Number 2, we saw what happened when we put a load, an electrical load, on the output of the windings here. It physically slowed down the rotor speed here as driven with my electric motor, simulating the tires and wheels of the vehicle, driving the vehicle. And number 3, we saw what happened when we connect the output of one motor to the input of the other to drive it. So neat stuff. Thank you for watching. Have a good day.